Hello everyone, so today our topic is about specific capacity and it's the second chapter in thermal physics 2. Okay, let's move into the first slide and here we have some details about specific capacity. So what is it? So before we learn the definition of specific capacity, we can imagine a scene in your mind. Okay, maybe it's now the summer and now you're walking near the beach, on the beach, right? And maybe it's a in the noon, you can find the sand is very hot. Okay, maybe your feet are very hot from the feeling very hot from the sand, right? And once you put your feet in the seawater, you'll find your feet then become cool, right? So we can find here the difference. In the morning or in the noon, you can find here is a sea and here's here's a beach. Or you can say here is sand on it, but here is sea and here's water inside of this, right? And on the beach, your feet is very hot, but here, if your feet standing in the sea water, it's very cool, right? So maybe let's switch another time, like you're going to the beach, maybe it's midnight, okay? And here you can find the sand on the beach is very cold, okay? Maybe here, right here, very, very cold, okay? And maybe the sea water you can find when you put your feet on it, this, and maybe here it's very warm, okay? Here is a difference, right? In the morning, we can find maybe here we can set the beach or the sand degree is 30 degree, right? And maybe in the evening, we can set that the beach degree maybe is like maybe 10 degree. Okay, okay. Like this is just example, okay? And maybe for seawater in the morning, it is about maybe 25 degree, and in the afternoon it's about 20 degree, okay? Or in the evening it's about 10 degree. Okay. So you can find that there have a same source, like there also the sun and the moon, right? So they have the same energy because the temperature and the time taken are the same, and they have the same sunshine under the sun, right? So we can say that the energy absorbed for the sand and water equals to each other, but they have a different temperature, right? So we can say that the water is very hard to increase the temperature and it's very hard to lose the temperature, right? And also for sand, you can find here it's very easy to increase the temperature and very easy to lose its temperature, right? So here, for the same energy, we can say the sand is very easy to absorb and release energy. Or like the water is very hard to absorb and release energy, okay? So we can say that the specific capacity means the ability to hold up the energy, okay? Or like contain, like it is a kind of uh, like a uh, like a container to contain the energy, okay? So we can say the water is a good container to contain energy, right? And to compare with the sand, right? So here is for the water's specific capacity. We can using this to represent for this, okay? So then you can find the formula here is energy transferred equals to the mass of the substance times the specific capacity times the change in temperature, okay? So maybe we can find if the specific capacity is very big, that means if you want to make a unit mass a substance to increase like a definite temperature, you can find here the energy transferred must increase, right? So for the water, you can find EC is bigger than the C sand, right? So maybe here it needs more energy to increase the temperature or need more energy to release its energy, right? So here you can find a table to represent for some very classic materials in our lab, okay? Maybe for water, we can find its specific capacity is 4,200, and for alcohol is 2,500, and maybe downward you can find the copper is 400, right? For the metals, you can find it's very easy to absorb heat and lose heat, and for like the water, alcohol, and ice, they're very hard to lose heat. And the IGCSE, we can say that water is biggest or it can contain the heat for the most ability, okay? So here we can say it's the most heat capacity or it has the biggest heat capacity, okay? Okay, and maybe here is the exercise. And for water, we can say that is C specific capacity equals to 4.2 times 10 third joule per kilogram per degree. And sometimes remember that a degree is not a like a SI based unit, but for Kelvin is a acid-base unit. So here we sometimes say Kelvin, okay? So here for this problem, we can say using the formula that the energy changes equals to the specific capacity times the mass times the changing temperature, right? Right here for this formula. So now you can using the formula to solve this, and you can using here C equals to 4.2 times 10 third, and then times the mass is 2 kilogram, and then times the changing temperature is 50 Kelvin, right? So here is for energy. And you can finally calculate this. It's about 4.2 times 10 fifths joule, okay? So here is for the energy. So we can say that the thermal energy can lose about for this amount, okay? And to remember that this formula is not only for absorbing heat, but also for losing heat, okay? This is for the like thermal energy here, okay? And for thermal capacity, this chapter is now deleted by the latest IGCSE syllabus, so you don't need to master for the thermal capacity, okay? So maybe here it just means for like we like doesn't consider about the temperature changes. We just consider about tying them together. Oh, sorry, we don't consider about the math, but also combine them together just to become like math times c. Okay. So here you don't doesn't you need to master this, okay? But for this experiment, it's very important. So I give you a figure right here, okay? So you can find this experiment is for measuring the specific capacity and how to measure this. And you can find here some apparatus in the graph. And first apparatus is there's a thermometer, right? And also here is a power supply. And we put them together in the water. And maybe here, if you want to measure the specific capacity, because it's not a very like useful physical quantities in our daily life, right? So for C, we can use in the formula like E equals to Cm times the changing temperature, right? Using this formula, okay? So maybe most of the time, if we cannot calculate very easily from apparatus, you can use the formula to like if we know that the energy changes, if we know that the mass, and if we know that the temperature changes, we can know the C, right? Using the formula to calculate this. And mass is very easy to measure, right? You can use a balance to measure the mass. And for temperature changes, now here we can have a thermometer, right? But for energy, it's very hard to measure this. But we can use in the formula before in the forces part we had learned before, okay? And it equals to the power times time taken, right? Here is a formula. So right here we can find if you maybe time is very easy for you to like calculate, right? You can use a stopwatch. And for power, we can set power just applied or like maybe for a constant electricity or like a constant like here we're using a heater, maybe the power is a constant number, right? Like you're using your iPhone, you can find the power for the charge of your iPhone is a constant number, right? So just make the supply or just make the heater becomes a constant power. That is okay. Okay. So if you're here, like using the formula, you can find a very constant power heat and then calculate the time, calculate the mass, and calculate the temperature changes. And then you can calculate the specific capacity. Okay. So maybe here you have a question. So, teacher Mai Lin, why here's a cover on the apparatus? Okay. So if the IGCSE P6 problem has asked for you for this, so please remind that before we have learned that about two like math ways to answer the question, right? Here are two advantages for like using the method or like using the apparatus or like using these ways. Okay. The first like usage is for increasing its accuracy, right? Increasing its accuracy. And maybe for a second reason, we can say that this is for the security, right? Okay. So here, maybe using a cover, I think maybe there is no reason for the security, right? Because we don't need to worry about like the beaker, right? Maybe you can say that beaker will explosion. Maybe here's a problem, but this probability is very low, right? So maybe we are choosing the first reason that it will increase in accuracy, right? Like using a cover, you can find is cover the total apertures. So like here, the cover can hold up the temperature and never let other heat to release or escape from the total apertures, right? So here is for the cover's usage. Okay, can you understand here? Okay. So here we're using the first choice that we can increase the accuracy. Okay. Okay. So after this, let's do a little bit problems. Okay. So maybe here you can try to solve for the question A, please. and think for several seconds, please. Okay, so maybe for this problem, I think it's very easy for you, right? You can use in the formula for density, like density for a substance equals to mass over the volume, right? So here, if we knew the density here is 1.2 kilogram per meter cube, so you can write it down here, 1.2, and mass, what is mass? And mass we want to calculate it, right? And for volume here, you can find the room is a cubic, or like here you can use in the formula 4.5 times 6.1 times 2.4, right? So here you can calculate that mass equals to 1.2 times 4.5 times 6.1 and times 2.4. And the final answer is 79 kilogram. So I think this problem is very easy, right? And maybe for a second question, you can use in the mass we have quoted before, that mass equals to 79 kilogram to try to solving this problem, please. Okay. Okay, I think you have your answer. If you doesn't finish this, you can just pause the video and try to calculate it and then review for your answer, okay? And maybe here you can find the power of the heater is 1,100 watt, right? And here the specific capacity of the air is 1,000 joule per kilogram degree. And calculate the time taken to increase the temperature of the air in the room from 60 degree to 20 degree, okay? So maybe here for this problem, maybe here you can find is just a calculation problems. Okay, you can use the formula E equals to the Cm dirty we had learned just now, right? And also another formula that how the heater will give the energy, right? That is because the power times time taken gives the energy. Okay, so using the formula, you can find how you calculate T. You can use in T equals to the specific capacity times mass times the changing temperature over the power, right? You can put the power at the bottom of the Cm dirty, right? And then you can just using the value to put them into it, right? And here C equals to 1,000. And for mass, it equals to maybe here, oh, sorry, 79 kilogram, right? And for the changing temperature, it equals to 16 degree to 20 degree times 4, right? And divided by the power. So here power is 1,100. Okay. So maybe here for this problem, I guess the value maybe 300 is around 350 seconds. Maybe it's more about this value. Okay. That's just an estimation for this formula. I haven't calculated this yet. Okay. So you can just try to use your calculator to calculate the final answer. Okay. Okay. So this is for today's our, oh, sorry. I guess it's not for 350. I guess maybe it's like around 300. Okay. Maybe it's near to 300. Okay. So here's for today's our lesson. Okay. Okay. So if you have any question, please feel free to ask me and see you next time. Bye.